they're taking discrete in Saxony and they're talking about a particular problem. Where they have to use the rect first search to find the largest number or the summation of the largest number in the tree, like that. Yeah, but you can basically apply the same thing as Dijkstra's algorithm to do it.
Damn, why does that sound so much easier? Dijkstra, D-J-I. I just said that.
D-I-J.
I'm pretty sure it starts with DJ.
D-I-J-K-S-T-R-A. Dijkstra. Just remember, I-J-K, they're in sequence. Yeah, Dijkstra.
Running some, I believe.
Yeah. So you have another array for the sum? No, I
You just have it on the node. Did you do it? I don't know.
No, I didn't.
So you made a node class?
All right, the recorder is on, and I am going to start this class. Cool. All right, so we are finally getting back to assembly language programming. And I think from the previous class, you guys realized how much trouble you have to go through to do the jump operation. So I'll go ahead and refresh your memory, making sure that we are recording this time, because I forgot to turn on the recorder last time, right? Okay, so see, I remember that I forgot. No, it is not an oxymoron. I can remember that I forgot something. Nobody's getting that one. Okay, so we are now in assembly language programming. So what I'm going to do today is I will give you a homework assignment. So there will be a homework assignment at the end of today's lecture, but only after I talk about the limitations of the current instruction set, because I want you guys to implement new instructions. Okay? So we'll make a slight change to the computer architecture itself, the processor architecture. That does not impact the width of the ROM, because that means a lot of work on my parts to rewire the thing. So I'm not going to rewire the thing. I'll just insert some special logic so that we can handle this slightly different case. But before that, we'll just go ahead and take a look at something that we looked at in the previous class that I forgot to record. Is that okay? Right? All right. So as you remember, hopefully, you go to the shared folder of this class, and there are 3 files that you need to download to use the processor in Logic. So we'll go ahead and repeat that process today, because now hopefully it is getting recorded. And let's see, where's my recorder? So the recorder is here, and we'll double check it is actually recording the voice. Yep, there we go. How many people use Linux in this class? Okay, we have a few. Okay, that's good. Okay, ish is fine. There's no problem with the ish. Okay, so I just want to bring this up because it is really kind of cool, because I found this program. Not this one. It's called OBS. It stands for Open. Is it open? Open Broadcast Software. And OBS is a studio also. So this allows you to do streaming. I set it up already using YouTube, and it works pretty good.
I saw the notification.
Oh, you did? That wasn't just a test. I wasn't really doing anything, but just, okay, press the button and see what happens. Sorry?
I saw that.
Yeah.
You saw that? Okay, cool.
I saw nothing.
Okay, so I might start to do that in my classes. I just have to be very careful. I have to ask each class before the semester starts to make sure that nobody needs assistive technology or closed captioning, because YouTube does its own closed captioning, but I think it may or may not work too well. Did I mention in this class that UC Berkeley had to pull 20,000 videos out of its library because 2 students from Washington, D.C. Wanted to watch the videos from UC Berkeley to do something, and then those 2 students turned out to be deaf students or hearing impaired students. And because the videos from UC Berkeley were not closed captioned, they brought the whole thing up to the DOJ, the Department of Justice. So the Department of Justice gave UC Berkeley an ultimatum and say, Either you close caption all 20,000 videos out there, or you take it off so that nobody can get it. So either everybody can access or nobody can access your 20,000 videos. Not just the ones that these two students need, okay? It's not like, the Department of Justice say, well, from here on, you guys really need to close caption everything, but for the 20,000 that you already have, just close caption the ones that these two students need, okay? On the demand basis. Nope, either you close caption everything or you pull everything off. Well, guess what you see that Berkeley did? Yep, pulled everything off. So now nobody can get to any one of those 20,000 videos. So I have to be careful. Okay, so basically OBS, allows you to do screen capture, sound capture, and it can stream everything to YouTube, which means I can be teaching this class and somebody can be watching the video from somewhere else with only a few seconds of lag time. And then YouTube can also save the entire thing at the end. If I do not click that checkbox and save the entire thing, I think most people can go back by 40 minutes or some really big buffer. So you can still go back in time, kind of like just kind of go back and review, a part of the video that is still streaming. So that's kind of cool. All right, getting back to this stuff here. So we get to shared, which you have access to. Then we go to processor. And the 3 files that you need to do your homework later on would include with DPC, direct PC, or with access to change the PC directly. But for now, we're going to ignore that. So we'll just grab the 3 files that we need, which is processor, ALU, and register bank. So these 3 files are the ones that we need for now. We'll do a right click and say download, which will give you a zip file, and then just unzip it and the folder will contain everything that you need. There we go, we saved the file. I'm gonna put it into, I'm just gonna call it processor, because I'm showing you guys what you need to do to get the homework started. So I would go to a command prompt here because I'm a command prompt kind of person, and make a new folder for processor. Go to the new folder called processor, unzip the file called processor.zip in the parent folder. Now I got all 3 files back, and then we just need to do a java.jar. You guys can just double click the jar file in Windows, and I think you should start it up too. I am doing it the command line way, which is the long way. There we go. And the file that you should start up with is processor.circ. Okay, so start with that file, press the enter key, and you'll be asked a few questions, 2 questions to be exact. Oh, no, I guess not, because they're in the same folder, so it pulled the correct register bank file as well as the correct ALU file. So now we have the processor back. Then we can start to write some programs to run on this particular processor. Are there any questions about the step up to this point? How you can start the processor emulation in Logic. The 3 files that you need to download, and also what it looks like when everything is loaded correctly. Is that okay? All right. Okay. So we'll go ahead and write a few programs, and we'll start with something that is relatively simple. When you write the program, you can use anything you want to, including Notepad, or you can use any type of text editor. It should be okay. Okay. So the emphasis at this point is the processor, but I will still show you how to translate code from C into assembly. Okay, because that's the objective in this class, is to relate C program, C and C++ code to the assembly language code that is behind it after compilation. Okay, so we'll go ahead and start with something like this. If x is less than 0, then x gets 0 minus x. So we are finding the absolute value of x and put it back into x. Okay. Or if you want to use a different variable to store the absolute value, you can say this is y. Then you have an actual else case where y equals to x. So if x is not negative, then y is just x, because y is supposed to be the absolute value of x. Is that code okay in C? Okay, no questions about this code in C? Can someone tell me what is the signedness of x and y? At least x. Is x a signed integer, or is it an unsigned integer? It's got to be signed, otherwise it cannot possibly be less than 0. Okay, so x has to be signed. Okay, and that will become useful later on. So we have to say x is signed, and let's just make y signed as well, because they should be of the same type. Okay, so let's go ahead and write the assembly code to do this. How do you get started with this? Let's deal with the conditional statement first. Okay, so let's just say that x is already in a particular register. So we'll go ahead and make some assumptions here. So we'll say register A, okay, register A is x, register B is y. So it's already given that I want register A to be x, I want register B to be y. So how do you get started with the compare? Okay, we want a CMP instruction. Very good. Okay, so let's start with that. Okay, so we want a CMP instruction to do the actual comparison. The CMP instruction can only compare values of registers. So it cannot compare a register to a constant. So there's no way for me to compare against 0. So what do I need to do first before the compare instruction because of that constraint? Yep, go ahead.
And move 0 into a register.
Into some other register. Very good. I can put it into register B because at this point register B has nothing to do. I only need to make sure that at the end of this code that register B is Y. So at this point I can use register B for whatever I want. So I can do LDI B with 0, which is load immediate. In other words, what I'm doing is I am actually copying the bit pattern of 0 into register B. Is that okay? So that's a LDI B0. Then we can do the compare. The comparison is AB, if I remember correctly, because I can never remember which way it is. I think it is AB to subtract B from A. Okay? But that does not do a single thing to tell me which one is larger, or in this case, whether x is less than 0. So what do I need to do at this point? It does set all the flags. So which flag do you think is important? Well, let's name the 5 flags that we have. We got 5 flags here. We got the sign flag, overflow, the L flag, the C flag, the Z flag. Which one do you think is important? The sign flag. The sign flag by itself is not sufficient because there are cases in comparison where the sign flag does not give you the correct result. The overflow flag is kind of the same way. By itself is not enough. So that points you to the L flag, because the L flag is the exclusive OR of the sign. Okay, the L flag is defined to be the sign flag exclusive OR the O flag. That's what we need. Okay, so when the sign flag is set, it means the first number is less than the second number using a signed interpretation. Is that okay? All right. So this is coming from way kind of back. Okay, when we first talked about bitwise operations in arithmetic, that's when we talk about the sign flag, the overflow flag, and the L flag. So we need to look at the L flag. So in this particular RISC processor, we can only do a JL. We cannot do a JNL, which means if the L flag is set, we want to go to the place pointed to by a particular register. So let's pick register, well, we can still use register B, because all you need is to make sure that you load register B with something first. Where should I go if the relationship is less than? I'll give you guys two labels to choose from. Okay, so I'll give you a label here called then. We'll give you a label here called else. So the question here is, should I go to then if the L flag is set, or should I go to else when the L flag is set? What do you think? Then, okay, sounds good. Sounds like it makes sense, because if x is less than 0, we should go to the then branch. Okay, what else do we need to do? Because that means there's a potential that this branch may not happen because it is not less than. So what do we need to do?
Jump to else.
Jump to else, very good. But since we don't have a JMP else instruction, we have to load B with else first, and then do a JMP to register B. In other words, we're using register B to update the program counter, and as a result, we continue execution where B is pointing to. Are we still doing okay so far with this stuff? Yep.
So why are we loading B with, so we load B with then, and then JL, what did JL do again?
JL will do the branch to whatever, okay, JL updates the program counter to B, whatever register B has, but even only if the L flag is set.
Oh.
If the L flag is not set, it will continue execution with whatever is next to it.
Okay, and so that it'll jump to then, right? So JLB, if L set, it'll jump to then. And so we'll be
Right.
ignoring the load else and the jump
Correct.
to else?
Yep.
Okay.
But we have to do the else part too, because otherwise it will fall through, which means it's going to do the wrong thing too. Okay, all right, cool. So over here, we're almost, getting to, okay, we'll deal with this one first. How do we subtract x from 0? We only have a subtraction instruction. We don't have a negation, arithmetic negation instruction. How do we do this? LDI, another register, pick, well, in this case, I'm going to pick B, okay, because I want B to be Y in the end, right here, so might as well just do it in B. So I'm loading B with a 0, and then we do a subtraction, BA, which means, this is subtracting A from B, but storing the result back into B. Isn't that what we want to store in Y? So we are all done. Almost, except we have to branch all the way to the end, branch around the else branch. Question? Yep.
Can you just change the sign flag?
Say again?
Why can't you just change the sign flag of X?
Because that does not change, that will change the sign of the number, but the value is going to change as well. Okay, so that's a good question. So we'll take a look at, an 8-bit number, okay? All ones is representing which number or which value when you interpret it signed. 2 is -1. Okay. So if you just flip the sign bit, it becomes 0, 1, 1, 1, 1, 1, 1, 1. Okay. Did I miss one? Nope. Okay. And what value is that representing as a signed 8-bit number? It's 1 plus 2 plus 4 plus 8 plus 16, 32, 64. So when you add up all those numbers, it's 127. So you cannot just flip that bit. Okay? You can use choose complement if you want to. That will give you the negation as well. But that's more steps than what we're doing here. All right, so we have a LDI, in this case, I have to use register C. We'll give it to the end, and end is just a label marking the end of the entire code over here. So,
So what we're doing, we're loading 0 to B,
uh-huh.
and then,
We subtract A, which is X, from the 0.
okay. And we do that only if it's negative, so then I put positive.
Correct.
Okay.
So now we only have the else case to deal with. So the else case is a little bit easier because all we're doing is just copying register A, which is X, to register B, which is eventually what we want to be in, what what we want to be representing Y. So a CPR would do it. CPR stands for copy register. So CPR AB would just make that copy. And there's nothing to jump around because this is already our else branch. It automatically flows to the end of this code. So there's nothing to jump around in this case. So at the end, it is usually good to specify a halt instruction because otherwise the program will continue to execute with the following opcodes. Most likely are zeros, which doesn't really hurt anything, but this way, it will just get stuck at this location. It's easy to tell that we are at the end of this particular program. Is that okay? No questions? Okay. If I were you, if I were sitting on the other side of this classroom, I would have asked a lot of questions. There will be a lot of questions. Yes, go ahead.
So we just know that there's a C, right? It's not like we can't just keep making up letters.
We only have 4 registers, A, B, C, and D.
Okay, we know we have those.
Yeah. Okay, so the next thing we want to do is to assemble this program. Okay, so we'll have to cut off all the C, part of this. So let me just kind of make a copy of this. Control C and paste. And then with the pasted version, I'm gonna get rid of all the C code. Do a really lousy job at it. Doesn't look good. It's okay. It will still be okay. Okay. And we can just copy and paste the remaining code, which is all in assembly. So do a Control C, copy, and then go to in the processor folder. There is a file called the assembler. So open up the assembler file, or in your case, you will have to make a copy first and then open it. Yep, go ahead. So you want me to go back to the other screen? There we go.
Yeah, so since register B is Y, set B to 0, how do you know what the original value of B is?
How do I know
The original value
of B is?
Yeah.
I don't really care because B is supposed to be reflecting the absolute value of X, which is register A. At the very end of this program, by the time we get to the halt instruction, I want B to be the absolute value of A. So I can trash B until this point. Yep, question?
So where are you making the labels for like else? Like jump there.
So when you make a label, you just spell out the name of the label, and then you just have
on
to.
that line.
Hmm?
And put it on that line.
Yep. Yep.
Is that an assembly language thing or the tax spreadsheet compiler thing?
It's both. So this is a general way to describe, to make labels and also utilize labels, but it's also the syntax that my spreadsheet recognizes. So my spreadsheet doesn't just come up with a syntax out of nowhere. It is actually borrowed from conventional assembly languages.
So like we're putting in conventional assembly language and it converts it to assembly language? I guess I'm a little confused.
It converts it into opcodes. Yeah. So when we get to the spreadsheet, it will be kind of clear what it does and what is the output of it. Yep.
Do the labels have to have a colon after them?
Say again?
Do the labels have to have a colon after them?
It must have a colon after that. That's part of the syntax. Yep. Okay. So let's go ahead and see if this would assemble. So once again, we just have to select the program, Control C to copy it. Go to the spreadsheet, and you can see that I made an entry today. I made a modification to the assembler today, and we'll be actually using that feature a little bit later on. Go to the source tab, and just go to the first line and do a Control V to paste, and it loses all the initial spaces of each line, which is not a problem. You do have to make sure that column B does not report any errors. In this case, there are no errors. Okay, let me just kind of quickly go over some of these tabs here. Let me resize this window first. Okay. Size. There we go. So this way, we can see the tabs at the bottom. So when you go to the Assemble tab, this is where all the magic happens. Okay, the details of the assembly is down here. It breaks each line into individual parts, and then it looks up the mnemonic table to figure out how to use each part and stuff like that. for the most part, you can just ignore this particular tab, okay? But this is where the assembling is actually happening. And then we get to the next one, which is the output. This one is reflecting, which address should have what content. So in this case, it's basically saying location 00 of RAM should have the bytes, 6D and then the 0. Location 2 should have the byte content of E1. Location 3 should have the byte content of 6D09. So these are the actual opcode corresponding to the mnemonics, which is the CPR, sub, CMP, those are called mnemonics. Is that answering your earlier question?
Not sure I understand it, but there was
Okay.
no time to learn.
So there's a translation process. The assembler is like a compiler. It is a translation. So it's basically translating the code which is in source like this. And by the way, you can also have comments in your code too. You can say initialize B with 0. Okay, it will take that. Okay, so // begins commenting of a line is recognized by this particular assembler as well. So it translates each line, okay, LDI B0 into 6D0. It translates the second line, which is CMP AB, to just E1. It translates LDI B and then the label then, wrong tab, into 6D09, and 09 is corresponding to the LDI instruction that is at address 09, and that's why in the output this is location 09. And that's also why we have 09 here, because we refer to the label in source, because we refer to the label called then over here. So later on when we figure out the label is actually at location 9, it knows that this is actually loading B with 09 as a hexadecimal number. Yep.
Little like spaces, line.
The empty lines do not do a single thing, but the output maintains the empty spaces, which is not a problem. I cannot make it ignore empty lines. That takes quite a bit of extra work, so I do not do that.
But if you were to change it, like, if you were to put that level to 8, would it be 8?
Yeah, it would update it. Okay, let's check it. So one quick and easy way to see if the label reference will update automatically is to put in a no-op instruction. Because a no-op instruction doesn't do a single thing, so it doesn't hurt the program, but at the same time, it does take up 1 byte, which is 00. So once you put in the no-op here, you go to the output, you can see that the address is now 0A, which is 10, and then this is also updated to 0A because the label definition has changed. So the assembler takes care of all of that counting, keeping track of which label is referring to which location for you. If you don't like doing this, you can always come up with your own opcode by hand, which was what we did in the previous semester as I was developing the assembler itself. Is that okay so far? Okay, yep.
You go back to the source slide.
Mm-hmm. The source tab, yep.
Yeah. So I still don't get the when you load B and you jump B, then
Okay.
Yeah. How
That's
you
okay.
use
That's
it.
fine.
Yeah.
So when you have a question like that, the best document to look at is, there are 2 documents, okay? So there are 2 documents that you might want to refer to from time to time. We're not doing I386 instructions, so you can just kind of ignore that one. But we are doing opcode for this processor. So this is the opcode table. So the opcode table explains, the various parts of a particular instruction. So for each instruction, it occupies 1 single row. For this row, the first column of the row, which is the first column, which is column A, is telling you the binary representation of that opcode. So I intentionally put a space between the 2 groups of 4 bits, because this way it's easier to read which one is the first four bits and then which ones are the second 4 bits. So in this case, it's 00, okay? And then the second column B, is telling you what is the mnemonic of that opcode. It is NOP for no op. And that's also what the assembler recognizes. Is that okay? So we have the actual opcode where the processor can handle. We have the mnemonic, which is what we can remember easily. And this is also what the assembler can translate into opcode. So for the most part, if you want to describe the assembler in one single sentence or in one single phrase, it translates from mnemonic to opcode. But it does throw in a lot of extra features, like keeping track of the labels, so that you don't have to keep track of the counting of the labels. The column C is one column here because I know you guys have all taken cisp310. So I want to explain the operation using C syntax. So in this case, with no op, it is simply an open and a closed curly brace, which is basically doing nothing. It doesn't change anything, it doesn't hurt anything, it doesn't stop either. It will just do nothing and then continue on. Is that okay? And then the fourth column is just a general description of what it does. So in this case, it's a no op. So now with the second row, it is the halt instruction, which is kind of equivalent to a exit one in a C program, which gets out of the C program. Another way to describe this is a forever loop, because it's just stuck. Okay, it doesn't exit. These are highlighted in a particular color because these will be the instructions that you are going to implement in your homework assignment. So by the end of today's lecture, you will get the homework assignment to implement all of these instructions. But we'll describe that process, okay? Because right now the assembler does recognize these instructions. It will translate a JLI into a 4-1 instruction. But the question is the processor going to execute that opcode 4-1 the way it is intended? And the answer is no, it's not going to do it because it doesn't recognize the opcode. The ROM of the music box does not have the place, does not have the specification to do this. So you guys will be helping me to generate the opcode, the microcode slices in the ROM as a part of your homework assignment. It may sound really difficult, but it's not, because I will give you a lot of tools to do that. Okay? So these are the instructions that you will have to handle. Many of the other instructions are handled already. Now there are instructions that will have the XXYY or just XX. So in this case, this particular instruction of the opcode is 0101XXYY. What that means is the 0101, which is a 5, is always there. Okay? The XXYY are used to specify registers. XX will specify register X, YY will specify register Y. So in other words, you have 2 bits to specify register X, which will give you the 4 registers. You have 2 bits to specify register Y, which will also help you specify the 4 registers. Is that okay or not? So the XXYY correspond to the XY of the mnemonic, and then the actual operation specifies that X is the left-hand side of the assignment, which means we are copying Y to X. Now what that means is, okay, we can use an example here. So let's say we have the opcode as 0101, and then the second part of the least significant bits are, let's say, 1101, okay? Can someone tell me which 2 registers are involved and which one is being copied to which other register? Well, pick out which one is XX first. The 11 is XX, so the 01 is YY. Okay, very good. So since we come from 0, 00 is register A, so 11 is register D. Yep, okay. So this is specified register D. And what about this one? Register B. Okay, so we have a CPR-DB, which is basically in C code, it is D equals to B. So we are copying register B to register D. Is that okay? Is the formatting understood? I mean, this is the bottom line is, do we understand the format of the documentation? Not so much how it is done at this point, but do we understand the syntax? Okay, go. Yep, go ahead.
The first part will correspond to some command like shuffle register.
0101.
So this actual instruction in RAM will be represented as 5, and this is D. So 5D, as 1 byte in RAM specifies that we want to copy the content of register B to D, register B.
Okay, so if you want to copy some other register, the first part will be the same, 0101.
Yes, because that's the pattern. So according to column A, that is the pattern of this particular instruction.
So how come GO and JS have similar left side? And JL is 01 and 0.
But that's okay, because I just need one single register to specify where it's going to. Right? Because I don't need register Y in that case. So I'm saving those bits to be used for other things. Question?
So what are the L, O, and S?
The what?
The L, O, and S and the J.
Those are the flags. The L flag, the O flag, the S flag, and then later on we'll see the C flag and the Z flag. So those are conditional branch instructions. Yep. Yes. PC is the program counter which controls where I'm going to get the next opcode. So by changing PC, you're changing the flow of the program. Okay, very good. Anything else? Yep.
This might be stupid. How many maximum opcodes can we have?
You can have, since we have 8 bits, you can have 255 individual opcodes. But opcodes are not always individual. In other words, if you look at A16 or the CPR instruction, we have a family of opcodes. So collectively, there are 16 variants of this. Some variants do not make any sense, like copying register A to register A, but it is one of the opcodes.
So how many categories do we have?
Well, we can count, because at this point we have up to here 32, and we have one line skipping here. So from 7 to 32, 32 minus 7 is 25, 25 minus 1 is 24. So we only have 24 actual mnemonic that you have to remember. Well, that's why it's called reduced instruction set. Okay, this is why it's called RISC. Okay, as opposed to cisp, where you have more than 200 mnemonics to remember. Yep. So this is fairly easy. Okay, fairly easy to remember. Okay. Any other questions? So when you look at some of these, yeah, go ahead.
Yeah. So when you say jump with L, then it will skip the.
Okay. So let me highlight the one that you're looking at, which is this one. Okay. All right. So when you look, so this is one of the few where when you look at the C notation, it is more helpful than just reading the description itself. Okay. So what this will do is it is going to change PC. It's going to change the program counter, potentially. The determining factor of whether we are changing the program counter or not is the L flag in this case. And we're using the ternary operator. The question mark and the colon is the ternary operator. So when the L flag is true, then we are going to use X, which is a register, to update the program counter. If L flag is cleared, then we're going to use the program counter to update the program counter, effectively not changing it. Is that okay?
Yeah.
Yeah. So that's why, with the conditional branch instructions, looking at the pseudo C code is actually more productive than reading the description, because it tells you exactly what is going to happen. Is that okay? Yep.
What exactly is the program counter like itself?
The program counter is a specific register that you do not have software control over directly, but what the job of the program counter is to track where is my next opcode to execute. It's a little bookmark to track where's my next page, where's my next page.
The path the program's going down, basically?
Yes.
Okay.
So without any branch or jump instructions, it will be always increasing, but sometimes it increases by 1 if your opcode only needs 1 single RAM location, but occasionally it will increase by 2 because certain opcodes require 2 memory locations instead of 1. Okay. Those are all good questions, very good questions. Okay, are we still working okay so far? Okay. All right. So these three is basically the same family. They're all conditional branch instructions. They're just looking at different flags to decide whether they're branching or not. This one is the LDI instruction. The LDI instruction has a very kind of strange representation. It is x equals to star and then in parentheses PC++, and it is post increment. So what it is really doing is, if you separate it into individual operations, is it will first do this, okay? In other words, it will go to whatever the program counter is pointing to, retrieve that byte and store it into register X. Now remember, X is either A, B, C, or D, okay? So you can update one of the 4 registers depending on which one you specify. And then what it will do is it will do a post increment, which means PC gets PC plus 1 to go over that to go over that particular RAM location. Is that okay or not? Mm-hmm. Because this is the only way I can put a particular value into a register. We need we need something to begin the value of a register, and this is the only instruction that can actually put a specific value into a register. And this is also an instruction that will take 2 RAM locations. So let's say we're dealing with LDI, I don't know, C with 2-1 in hexadecimal, okay? So let's say this is what we want to do. The first thing we do is we look up the opcode table and we say, okay, LDI is 0110, 0110, and then 11, and then XX, okay? In this case, XX is corresponding to register C. 0 is A, 101 is B, so 10 is C. Okay, so we know these XX should be 10 in this case. But we also need one more location in RAM to specify 221. 21 is 5 in hexadecimal, which is 0001, 0101 in binary. So this one single instruction will take up 2 bytes. The first one is the opcode to tell us what we are doing, but we need a second byte to store the value that we are going to copy into register C. Is that okay? Yes.
Same line or?
Yes, you have to put them on the same line, with a comma separating those 2. We have been using the LDI instruction.
Yeah, but the Opcode side.
Well, the syntax of the LDI instruction tells you how to use the LDI instruction. So it tells you that the first thing has to be the register because it's an X, and then the second thing has to be is an I, which is an immediate value. So that's a number or a label. Yep.
So based on the sign, will we know the PC value?
Okay, so let's say we're dealing with JS, okay? So JS, okay, let me find a clean spot here. Okay, so we're dealing with JS, and we'll give it some specific value, okay, JS B, okay? So what is it doing? It is equivalent of doing something like this. If the sign flag is true, then we say PC equals B, else PC equals PC, which is basically the same thing as not having else itself. That's just the ternary operation to specify exactly the same thing as what we do here.
But I mean, like a PC equals the program counter.
Yes. And whatever B register has, PC will also have that. But what is the job of the program counter? It is where we will find the next opcode to execute. So you're changing the flow of the program to whatever B is pointing to. When we look at the actual architecture of the processor, actually, this is the better way to explain it. PC is over here. This is PC, okay? So the question is, what do we use PC for? Okay, so you track down the output of PC. Okay, so here's the output of PC. By default, it goes into an increment mechanism, right? Because there's an adder, it goes back to PC itself. But where does it go to other than the increment mechanism? It goes to mux. So it goes to this mux, right? So you have to now look at the output of this mux. The output of this mux goes to the address bus of your RAM. In other words, PC can directly control the address port of RAM. Is that okay? And then what we'll also do is, when we use PC to address RAM, we can take the content of that location and put it into the instruction register. Whatever you put into the instruction register is whatever instruction you're going to execute next. So the program counter is basically keeping track of where's my next opcode to execute. And normally it's just incrementing, which means you're just executing the program sequentially. But if you change the program counter, you can continue executions and skip certain opcodes, or you can go back to an earlier location, making a loop. Is that okay? Okay. Well, let's go ahead and make a program to illustrate that point. Okay. Let's make this one of the smallest infinite loop programs. Okay. This may not be the smallest, but it's probably darn close to the smallest. Okay.
You have to run the first one, right?
Yeah, it's okay. We'll do that later. But I think it's important to write the simplest program to illustrate it first. So we'll have LDI. Okay, we'll have begin as a label. Okay, LDI register A with begin, and then JMPA. Okay. Does everybody agree that this is probably one of the shortest infinite loop that we can write given the current instruction set? Okay. All right. So let's go ahead and copy and paste it into the assembler. Okay. So we have to make sure that this goes back to where is it? Assemble source. Go to line 1. You can leave the rest here, even though it's kind of distracting, or you can just delete it, which is okay. Then we can go to output. So this particular program will have 6C, 00, and B1 as the bytes. But in order to, you can do this manually, okay? If you don't mind typing into the RAM content of the simulator, you can do it manually. 6C, 00, B1, okay? So you can go here. Before you do that, I would recommend that you click the reset button first, just to make sure that everything is in the reset state. And then we specify 61, oops, click first, 61, 00, and then the last one was what? B1. Huh?
6C.
Oh, it's a 6C. Oh, okay, 6C. And this is why you don't want to do the copying manually. What do you do when you don't want to do it manually? Well, fortunately, there's one more tab. Okay, 2 more tabs, but this tab is the useful one. So this tab gives you the content of a file, a text file, that you can just import into the RAM module of LogicSync. Okay, so the trick to do that, I'm pretty sure we're still recording. Double check. This is important. Okay, it is. We're still recording. I think streaming is better because just in case something catastrophic happens right now, like an asteroid hits this classroom, but in that case you wouldn't need the recording anyway. So let's say there's a micro asteroid just hits me, okay, or better yet, just hits my solid state hard drive, okay, because that's the only thing that has to break in order to make my point. If I were streaming, then YouTube will still have everything up to a few seconds before the asteroids attack. Yep.
There is a downside to streaming. You're now vulnerable to internet problems.
True.
So if campus has internet problems.
But I'm using Google Document to begin with.
Right, but we're not always on the internet. Is all I'm
True.
saying.
Yep. It's okay. We are wired more so than we think we are. Okay, so the way to do this is to download it. And you have to download it as a comma separated value. and just click Save File, click OK, give it a name. I'm going to say this is loop, okay, loop.csv. You can change the extension, it doesn't really matter. I changed it to loop.ram to kind of emphasize this is the content of RAM in Logisim. Then you switch back into Logisim, go to the RAM module, and to illustrate it, let me just reset it one more time so that we can clear the content in RAM. Okay, so go back here, RAM is now cleared, right click, go to load image, go to the same location, which is /temp/loop.ram in this case, click open, and we get the content back. So that's the more reliable way to do it because you're relying on the software to give you the file to import into it instead of hand copying everything. Okay, so now that we have this all done, what are we going to do? We're going to trace the program. We're going to run the program, right? Okay. But when you run the program, you might want to run it very, very slowly first. Okay? And you want to observe, what is happening with the entire processor. Because the first thing you want to do is to track down the important registers. There are a few registers that are really important. The first one is PC, the program counter. Because the program counter is hooked up to the reset line, it also means that when you hit the reset line, the program counter is automatically reset to 0, okay, just like all of the other registers. The second register is the microcode pointer register, which is this one here. Once again, this one is also hooked up to the reset line, but the reset of this line is an OR between the actual reset line and also one of the output of the ROM, which resembles certain things of your music box design. Okay? In other words, whatever you specify as the content of the ROM can reset this particular pointer, which is really important in this case. So now we can see that, we have this content here in the first location, which is location 000 of the ROM. It is 108.0007. What does that mean? Well, if you really want to figure out what this is doing, then you will need to translate this entire number in hexadecimal into binary. Okay? It will translate into a 26-bit binary number. Okay? The 26 bits will correspond to bit 0, which is all the way up here, down to bit 25, which is down there. Okay? So where are those 26 bits going? What do you think? Do you think it's a big secret that you have to kind of dig up or ask someone? Or do you think you can track it down yourselves? You can track it down yourselves, okay? So we'll just do this one, okay? So we'll track down 25, okay? Where's 25 going? 25 is a dark green color, which means it's a 0. 25 is going into the OR gate, and together with the negated state of the reset line, we are not changing the microcode pointer back to 0, okay? So that's what 25 is. 24 is this wire here, and we track it down to the mux, and this is the input of the mux, or the selector of the mux. Because it is a 1, we're selecting input 1 into this mux. Input 1 is in the incrementer, from the incrementer of the microcode pointer, which means when I do update the microcode pointer, it is going to be going up by 1. And then we look at Ucode data is a whole bunch, we'll deal with that later. This is RAM select, or this is RAM load, excuse me. RAM load is a tunnel, because I don't want to run wires all over the place. But RAM load is a 1, which means we're reading from RAM. What is the next one? RAM select is a 1 because we are addressing the RAM. We want to say, hey, RAM, we need to do something. So that's why RAM select is a 1, because now we want RAM to respond to all of these other signals. And then 0, bit 0 is this guy, is going into this particular part here. It is enabling the instruction register. Can anyone tell me what is the enabling part? What does the EN or the enable port of a register? What does it do? Sorry?
Allows it to be modified.
Allows the next clock cycle, the next edge, to update the content of the register. Next rising edge by default. Yes. Okay. Very good. Good job. So we are basically setting up everything, to read from RAM, to update the instruction register, and use the program counter to specify the location. How do we know that we're using the program counter to specify the location? Well, let's track down a few things, okay? So what we need to do now is to look at this bundle of wires called Ucode data, which is translating into here, and track down each one. You can see that this wire is dark green, which means RIMux is turned off. Okay, we are not using the register bank at all, so we are not specifying which register, how we update the register bank. RIEN is disabled, which means we are not updating any registers in the register bank. And because we are not updating any registers in the register bank, the select pin doesn't do a single thing. We are not enabling register bank output 0. And as a result, the select pin also does not do anything because we are not even enabling the output of the register bank 0. The demux doesn't do a single thing either because we are not using that output. Same thing can be said about register output 1 of the register bank. We are not enabling it. And so the mux and the select do not really matter. The ALU is also disabled because the enable pin of the ALU is a dark green, it is off. So that means whatever we specify as an operation doesn't matter because it's not enabled. The address mux is a 1, okay? So this one is important. So we need to track down what it does. So address mux goes into this particular mux here, which means since it is a light green color, it is a 1, which means we are selecting input 1 to become the output. Input 1, guess where it's coming from? It's coming from the program counter. It's coming from PC. So this is how we can track it down and say, oh, so we are using the program counter to specify the address, and then we are reading from RAM in order to update the instruction register. Okay? And also, we also want the microcode pointer to increment by itself to go to the next location, because it is wired at this point to go to the increment mechanism instead of going from the instruction register. Is that okay? So you can look at all of these wires and figure out what each slice of the microcode is going to do with the processor. This is your music box, except it is far more complicated than the music box that you did as a homework assignment. But the mechanism is basically the same thing. It's just what is it controlling. It's not controlling a 7-segment display anymore. It is now orchestrating all the various parts of a processor so that we can, if you look at this from the, what is the name of that children's show, the Thomas the Train?
Shining Time Station.
Huh?
Shining Time Station.
No, but the name of the show?
Yeah. Thomas the Train?
Thomas the Train? Thomas the Engine?
Yeah, well, Thomas the Tank Engine was the character.
Yes.
It was called Shining Time Station.
Okay.
Thomas's Friends is also
Thomas and Friends, that's it. Thomas and Friends. So imagine this whole thing, this entire diagram is the island where Thomas, all the stories happen. So what this is doing is the conductor, making changes to all the switches in order to control which trains go from which station to which station. This train gets to cross the bridge, and so on and so forth. That's what this this music box is doing. But nonetheless, it is still quote unquote a music box, where one bit is controlling one particular thing, and sometimes you have several bits to specify one single thing. But it's the same idea. Is that okay so far? I know by the end of today's lecture, people can only remember Thomas Train, Thomas the steam engine, and none of these actual processor stuff. Which is probably still okay. All right. So we'll go ahead and single step, okay? So we'll control T and single clock a clock cycle, and then clock it one more time. There we go. Okay, so now we are on to the second instruction. Why did we move from the first or 00 to 000 to 001? What allowed it to change to the next location? The auto increment, exactly, the auto increment of the microcode pointer. Okay, so now we have a different pattern. So once again, you need to look at this entire pattern and figure out, okay, what is this going to do? okay? All right, so let's go ahead and take a look at what this is going to do. We are still not resetting, okay, the instruction. In other words, we are not resetting the microcode pointer. Okay, good. We are still selecting, oh, look at this one. The select line of this mux is no longer a 1. It is now a 0. So that means we are not going to take this input, which is the incrementing value of the microcode pointer. We're not going to use this to update the microcode pointer anymore. We're going to use this one to update the microcode pointer. This is big. This is important. Because now we are saying, but where do we get that value? 0, 1, 1, 0, 1, 1, 0, 0. That sounds vaguely familiar. What is that? That's 6C, okay? That's the one byte that I typed in incorrectly. I typed in 6.1 instead of 6C, and you guys corrected me, right? But it's not 6C either. This is 6C0. We got 4 bits padded in as the least significant bytes. Did you guys see the mechanism to pad in those 4 zeros? It's because of the splitter. Okay, so in the splitter, we specify bit 0 to 3 as zeros, and then we specify bit 4 to bit 11 to be coming from the instruction register. Let's track down the instruction register. So the instruction register is over here, and it has a content of 6C. How did it get 6C? We read it from RAM, exactly. This is the first byte of RAM. Okay, very good, good job. Okay, what else are we gonna do? Let's figure out the rest of all of these bits here. This one says, we are still using RAM load, but we're not selecting RAM anymore. In other words, for this particular clock cycle of the music box, we are not reading RAM at all. Okay, we're not using any part of the RAM. I have to specify a value for RAM load. I just chose to use 1. Okay. What else are we doing here? Address mux, that's not important. PCEN is important. Okay. PCEN is the enable of the PC or the program counter register. In other words, I'm ready to update the program counter. Okay, that's important. How are we updating the program counter? The program counter has its D port or the input coming from a mux. The mux is selected by PC mux, and PC mux in return is coming from here. This is PC mux, and PC mux is the result of this particular mux here, which is controlled by PC mux mux. The mux that controls PC mux is PC mux mux. Okay, and PC mux mux has a value of 101. So that's why it is using this as the input, and that's why PC mux has a 0. Now the reason why this is so complicated, where we have a PC mux and the PC mux mux, is going to be apparent when we have to deal with conditional branches. This part here is set up to deal with conditional branches. But at this point, we are not doing conditional branches. All we are trying to say is, okay, let's make PC mux a 0. That's basically the bottom line. But PC mux is a 0 only because PC mux mux is 101, and PC mux mux is a part of the ROM of the microcode, because you can see that PC mux mux comes from right here. So it is a part of this content here that we store in the ROM. Are we doing okay so far? So what are we doing to the program counter? The program counter is using port 0 of the mux to update itself, and that is connected to where? It's connected to the quote-unquote adder. Okay, very good. And I said quote-unquote here because sometimes it is an adder and other times it is not an adder. Whether it is an adder or not depends on PC Inc. Because PC Inc. is the carry bit, CN, right? So which can be 0 or 1. So if PC Inc. is a 0, the program counter is not updating because it's adding 0 to itself. If PC Inc. is a 1, then it's going to increment and increment to the next location. So we do have a programmable way to specify, are we staying at the same location or are we moving on to the next location? In this particular case, you can see PC Inc. is a light green line, which means it is in fact incrementing to the next location. So in the next clock cycle, program counter is going to increment. Yep.
So is that there so that is that for halt? So you whenever you do the halt command?
It's not just for halt, it's also for the conditional branch instructions. So in order to understand that part, you can click on PC Inc. and see which part of this diagram is updated. And you can see PC Inc. is here. So it is also for conditional branches. So in the conditional branch, what it will do is it will take one of the flags and use that flag to specify PC Inc. so that we can specify, are we changing the program counter or not? Okay. All right, so we got two things going on right now. Two things are going to be updated, two registers. Because when you look at the registers, whatever register that has an EM being highlighted with a light green line is going to be updated. The program counter is going to be incremented, and then the microcode pointer is also going to be changed, but not incremented because it is going to be changed to whatever the instruction is with 4 zeros padded to the right hand side. Are we doing okay so far with this? So the program counter incrementing simply means, oh, we have just decoded an opcode. It's now time to move on to the next location. We know what to do with this one already. Let's move on to the next one. That's why the program counter is incrementing, because we have just loaded the content pointed to by the program counter into the instruction register. We have made use of the program counter, so it's time to move it on to the next location. The second thing is the microcode pointer. It is not incrementing because now we are quote unquote decoding the opcode. Decoding the opcode is exactly what we are doing right now. We are taking the output out of the instruction register, which is this wire here, pad 4 zeros to the right hand side so that it becomes 6C0 in this case. And then in the next clock cycle, Control T, you can see microcode pointer is now 6C0. Is that okay? Can anyone guess what is at location 6C0 in the microcode ROM? It's not jump. 6C is Ldi instruction. Sorry? It's going to specify a register to be updated by whatever the program counter is pointing to. Well, don't take my words for it, right? So let's check it. Okay, how do we check this? I remember what I said. It is going to specify a register, and which register to be exact? 6C is specifying register C to be updated to the content of the RAM module pointed to by the program counter PC. That's what I said, which is also the description that we have here. And we are trying to do this right now at this point. Register C is updated by whatever the program counter is pointing to in RAM. Okay, how do we check that? Well, we look at the register bank. It should tell us something about something being updated. Okay, so when you look at the register bank, which is this particular thing here, is it telling kind of right away, just by looking at the color of the lines, is it telling you that something is getting updated? RIEN, register input enable, is a light green, which means we are updating one of the registers inside the register bank. To figure out which one is actually getting updated, you kind of have to click it. And since I cannot click the wire, but this wire would have indicated 10, which is register C. Okay, RISEL is going to be specifying register C, or it has the content of 10. We can click it here. That's fine. Oh, it's 00. It's register. That's a select. Sorry.
Aren't you doing the infinite loop here?
Oh, right. I'm doing the infinite loop. So it is register A that we are updating. So, okay. So this is correct. RISEL being 0 is fine. because we are updating register A. Okay, so now are we reading RAM? How do we know that we are reading a location in RAM and use it to update the register? Exactly. So register our RAM cell is a 1, which means we are telling RAM module, hey, we are talking to you. We have RAM load being a 1, which means we're reading from RAM. And so we know that this wire is driven by the RAM module. This particular wire goes to many places, but one of those places is this mux here. If this mux is a 0, has a 0 as a select, this is now connected to, this wire is now connected to this wire over here. In other words, we are using the content 0, which so happens to be at location 1, because program counter is 0, 1, to update register A. Are we still doing okay so far with this? Okay. How do we know we're using the program counter to control the address of the RAM? We look at the program counter, and we look at the output of the program counter. It doesn't connect directly to the address bus. It does go through a mux. But when you look at this mux, you can see the address mux being a light green line, which means it's a 1, which also means we're using input 1 of the mux instead of input 0 of the mux to serve as the output. Input 1 of the mux connects to the output of the program counter. So that's how we know that 0, 1 is also on the address bus, and that connects to the RAM module, and that's why location 1 is now selected, and its content is presented into the D port of the RAM module. Is that okay? But this is how you can look at each instruction and find out how it is implemented. Every single instruction, all 24 minus the 5 that you're going to implement, the other 19 instructions are already implemented. And they're all implemented by specifying these individual slices in ROM. Are we doing okay so far with this? So your job as your homework assignment is to implement those 5 instructions that are highlighted. Okay? So we'll take a look at those 5 instructions. And those are in your opcode description. If you scroll up, the highlighted ones are the ones that you have to implement. So how do you get started with this? Well, there are 2 things, okay? The first one is you're not going to use processor.cert because that's the old one. There's a new version of the processor. So the new version of the processor is called processor WDPC with direct program counter, so that we can change the program counter directly. So you will want to download this one too. So go ahead and download this one. And we'll save it to the home folder. We'll put it into the processor folder. There we go. And I specifically use a different name so that these 2 cannot confuse each other. And then we'll take a look at the new one. And I'll go ahead and flip-flop between these 2 so that you can compare what did I change. Okay, so we'll go ahead and find out what we changed, what I have changed in this particular one. I think we can do it in Logisim too. You can open 2 different files and keep them separate. So we'll open it again. And this is going to be in my home folder under processor. It's this one here. Okay. So very quickly, can someone tell me what I changed? I think, there we go. Okay, so this is before, this is after. This is before. This is after. There's a very small change, okay? The very small change is what do we need to feed, what do we use to feed into this mux with input 1, okay? So look at this wire, okay? This wire is the only one that is changed. In the new one, this is the same wire. So in the new one, the wire is not going through a mux. The mux is going to the register output, just like before, but it's also going into the data line of the RAM. Okay, and then the select is not a new pin. I did not create a new pin in the ROM. It is coming from an AND gate. So the AND gate is saying, are we a certain PC mux? If so, that meets one of the requirements. Are we also negating our register output 0 enable? So when we have PC mux being a 1, now PC mux is also used here. Can you see why I use PC mux as a part of this AND gate? Because what happens when PC mux is a 0, like what it is right now? Then we're going to use the other wire anyway, so whatever that mux, the new mux is doing, doesn't matter to me, okay? So that's why I use PC mux as a guard condition. Okay, so fine, let's say PC mux is a 1. If PC mux is a 1, then we are using this particular wire to feed into the program counter. So that becomes important. And then this wire is negated. In other words, if I choose PC mux to be a 1, but RO0 enable to be a 0, then I'm going to use, this becomes a 1, and when that becomes a 1, I will use this wire to connect to this wire, and that wire in return connects to here. But where do you think this wire is going to? Well, you can already see the rest of this wire. It's going to the data port of RAM. In other words, I'm connecting the data port directly from RAM through the 2 muxes back into the input of the program counter itself. So I'm using the program counter to say, hey, program counter, use whatever you are pointing to right now in RAM and update yourself with that content. Is that okay? All right. Okay, we've got 5 minutes left. So that's the only change, but in order to do your homework assignment, you will have to use the new processor design. The old processor design does not have a pathway to connect the input of the program counter to the data port of RAM at all. So you have to use the new one. Is that okay? All right. So knowing this, and going back to the instructions, let me go back to the slides here. Going back to the instructions. Do you think you can borrow some of the opcode as a hint to get this done? In other words, do we have something that you can kind of look into and go like, well, it has kind of what I want, but not exactly what I want, but pretty close? We have the jumps. Okay, what about dereferencing the program counter? Something like dereferencing the program counter. Do we have anything that dereference the program counter? What do you think about the LDI instruction? The LDI is right here. Also here. So when you look at the microcode of the program counter, of the LDI instruction, and you look at the instructions of the regular branch instructions using a register, you kind of merging those two. Okay? And then somebody's going to complain and say, I don't want to mess with bit shifting and doing all the ORing and figuring out how to, get everything, put everything back together. Right? I mean, I would raise my hand right now and say that, no, I don't want to waste my time counting bits. Okay? Which is perfectly okay. So that's why I'm allowing you guys to use my program as a basis. Programs in plural. This is a tar file. It says opcodes.tar.gz, which means you have to use 7z or 7zip to open it in Windows. If you have a Linux box, it's easy. Linux box just untar. Okay, tar xzvf and blah blah blah. Okay, so let me show you what it has, because it has pretty much a lot of your answers here. So I'm going to download this file and put it into my processor folder. Okay, so that's fine. Let's put everything into the same folder right here. Save. Go to that folder. And now we have opcodes.tar.gz. So in Linux, you just say tar xzvf. I like the v because I like to see what files is created in the process, but it's not required. Opcodes.tar.gz, and it creates its own folder called opcodes. and a whole bunch of .c files. When you look at the names of those .c files, what do you recognize? Yeah, those are the mnemonic names. So that means if you're going to create 5 files, right? JLI, JCI, JZI, JOI, JSI, and JMPI. Okay? But you're not going to create those files from scratch, because you can just copy some of my files and then make changes to those. Okay? So what we'll do next is to look into this opcode file. And for those of you who use code blocks, I am sorry, you probably have to use the command line tools in this case, because there's a make file here that will make everything. Okay? So when you look at the make file, it has all kinds of stuff, but the ultimate target that we want to do is called all.rom. Okay? So what you want to do is you want to change opcodes over here to include the files that you're going to create. Okay? So let's just say that I'm creating a JMPI in this case. Okay? So you add one at a time. You don't have to add all of them at the same time. So I'm just adding JMPI, in this case. And then I just say, well, I'm going to use jump as a basis for JMPI. And then I take a look at what is in JMPI at this point. This is the entire program. What do you think these things are representing? Okay, first of all, what do you think B1 is representing in this case? Remember, we're dealing with, this is copied from JMP. So what do you think B1 is representing? If I'm not explaining to you, what are you going to do next? Look at the definition of those subroutines, right? Okay. But if I tell you, if I look up the table of the opcodes, and we'll look up JMP itself. JMP is, where's JMP? Come on, right here. Okay, so what about JMP that reminds you of B1? That's B1 right there. In other words, the base of this opcode is B1, except the bits XX can change it into the variants of B1, B8, B4, B8, BC, and B, okay. I have to actually do it. So it's going to be B1 to use register A. It's going to be B9 to use register B. It's going to be B5, sorry, 5, because we're adding 4 for each one. Yep, we're adding 4. So 5 plus 4 is 9. 9 plus 4 is 13, which is a D. And then 13 plus 4, no, that's it, C, D. So these are the variants of the jump instruction. B1 corresponds to JMP A, B5 corresponds to JMP B, and so on. Is that okay? So the B1 in the C code is the base code of the instruction. Do we know the base code of the instructions that you need to implement? Yes, we do. Do we know those in hexadecimal? Sort of. I gave you the binary representation. You have to convert it into the hexadecimal representation. Okay? So that's what these, the B1 is for. Okay, that's where the base code of the instruction is. This is how many bits you have to shift for the X. Okay? Do we use the X register in this case? Nope. So what do we do to specify no X register? Well, if you look at this, it might give you a hint. But if you're not convinced that this is telling you what to specify to say do not use X, let's look at another instruction that has no registers. Which other instruction does not use any registers? Which instructions, in fact? The halt instruction doesn't use any registers, right? So you can look at the halt instruction and say, how do I specify this instruction does not use any registers? What do you think? No XX instead of the 2. Is that giving you a clue of how to get started with your homework? Okay? So what you're really doing is you are just changing this particular code to specify the bit pattern that is needed in order to implement the jump immediate instruction. You're not using any registers, but which instruction uses whatever the program counter is pointing to? LDI. LDI is the only other instruction that makes use of the reference of the program counter. So it might be helpful to look at that one, right? So you look at LDI.C, and that one, has some kind of specification that it's using register X in this case, but these bit patterns are corresponding to what? What do you think? Okay, I'm passing slices to write slice. Okay, so you want to look at what write slice is going to do. So let's take a look at that particular source code. Okay, write slice ucode.c. Oops. All right. So, do you think this is going to be helpful? It's telling you the ordering of those parameters that you're passing into, that you're specifying in slices. Okay? In other words, they're all spelled out, including the names. And these names correspond to the names used in the schematic of the processor. Is that okay?
Now we just need to figure out which one is 0, which one is 1.
Exactly. Yep. So when you look at the actual write slice subroutine, okay, write slice is right here. So this is the actual write slice subroutine. Do not change it, okay? But what you do need to know is how am I using the slices, so you can see how the slices are being used correspond to this little table here. So look at Ucode, okay? So I'm going to use you look for Ucode, and you can find out how Ucode is used here. Okay, so Ucode has individual fields to define the offsets, and it's using bit field index. Bit field index is going from 0 to 18, and those are also corresponding to something that is the input of this subroutine corresponding to slice. So that's how you do it, because you can see how slice is using bit field index to index into that array, and you can also see how Ucode is using bit field index to index into that particular array, which basically means element 0 of slice as a parameter is corresponding to element 0 of Ucode as an array that is already initialized. So you just have to basically look at Ucode microcode pointer reset. Is it a 1? Is it going to be 0? Specify that. Next one, look at Ucode pointer select. Is it going to be a 0 or 1? So all you have to do is to kind of initialize those values, and then make your slice array in main, pass that into this subroutine, and it will do the rest. So it will do all the bit shifting, converting everything into hexadecimal and all that stuff. Are we doing okay so far with this? At least the general idea. You do have to read some of my code to get this done. Yep.
You want to turn in 5.c files that have these?
Yes. You want to keep this structure. Okay, so what you want to do is eventually you will have jump I, JLI, JCI, and 5 additional things at the end of this line, right?
I'm asking, do you want to turn in a chart, GZ file that has all this backed up together?
That's a good question. I would like that. That would be fine. You can also just turn in the 5 individual files. I can deal with that as well. So I haven't really quite decided yet. So when I write the actual instructions, I will make that clear. But for now, the way you get started with this project is to implement one instruction at a time. Okay, so when this is all done, when I'm done with implementing one instruction, what do I do to test it, right? That's the next instruction you're gonna have. Okay, so let's say I'm done with the JMPI instruction. So I'm gonna make some changes to the JMPI instruction. I'll just throw you a freebie here. Instead of a B1, what should this be? According to the spreadsheet here, JMPI is supposed to be a 4.0, okay? So the base instruction code is a 4.0. It is only going to use one single byte, so it takes up, well, how many slices it takes up is kind of up to you to decide, okay? I'm not really sure how many slices it's going to take up. I'm thinking it would take up 2 slices, possibly 1, okay? So, that's up to you to decide. We know that this is not going to use any X register, so we will say no X register. So I'm not changing the slices over here because that really is the main part of your homework assignment. So I'm not going to do that part. So remember, you have to change this. Okay. So let's just say that we're done with this one. What you do is you say make, and that's it. This is magical. Oh, okay. It says there's a link time error, undefined reference to make ROM, write slice, write ROM. Why is that? Oh, I remember. Okay, so in your make file, you also have to add one of these entries here because it has to link with the other files. So every time you add a new instruction, you have to kind of make a copy of that here, and then say JMPI depends on JMPI.o and the other 2 files because it has dependency on the other 2 object files. So 2 places to edit every single time you add a file here. The first point to edit is opcodes. You want to append the source code of the file that you're adding here. The second thing you have to do is to copy and paste one of these lines, doesn't matter which one, change the name of the target to the object, to the opcode that you're implementing, to the mnemonic that you're implementing, and then change just the .o to the opcode or the mnemonic that you're implementing, but keep the other object2 files the same, okay? Okay, so now we just say make. All right, magically, done. Okay, the output file of this is all.rom. And what do you think all.rom is going to contain? The actual content of the instructions in the ROM. So if you just use an editor to look at all.rom, it's not pretty, okay? But it's okay. It's not intended for humans to read. It's intended for Logicsim to read. So now you put it into Logicsim, okay? So you go to Logicsim, you go to the ROM module, right-click, and then say load image. So this time we are loading it from the all.rom, okay, which is from all.rom is right here. Open. So now we have that new instruction implemented. So you just have to design a program to test it. Is that okay? But how do we know it is actually in here? We want to double check. So what you do is you go to edit content, go to location. Which location should I go to check whether that new instruction is implemented? What is the base code of that new instruction? 4.0, right? So which location should I go to? Not 4.0, because we are adding 4 zeros to the right-hand side of the actual opcode. 400, exactly. So it's not 400 because it's not a base 10 number. It's 400. So you go to 400 and we have something here. Okay. So the program worked. Okay. The make file worked. We do have something here. Does it implement what it is supposed to? No, because I didn't change the actual bit pattern. Okay. So this is still doing exactly the same thing as what a jump instruction would do, not jump immediate instruction. But that's your homework assignment, is to figure out which bit to change, and how many slices it's going to take to get this done. Is that okay? I'm going to give you guys up to next Thursday to get this done. So we'll have 2 additional classes of meeting, okay? But I would strongly suggest to get started today. Get all the pieces first, okay? Get all the pieces. read the code that I have already written, because you're gonna borrow a lot of that, okay? So you're gonna borrow the infrastructure that I have set up already in order to just change a few bits to implement the new instruction. Okay, so I'm gonna head out to the lab. I'm pretty sure some of you will want to get started right away. So I'll help you guys to get started.